Hello, welcome to Math Learning today.
And welcome. Welcome back. So today I want to share with you some of the fun things I've noticed since I moved to Collingwood. In my neighborhood, it's just like so many bunnies in that neighborhood. It's delightful, but it's beginning to be a problem. Like 2 years ago, I noted carefully that there were 400 bunnies. Last year, there were 460 bunnies in my neighborhood.
How many?
460, right there. See, it's on your sheet too, in front of you. And then this year, 520 bunnies. It sure is. Is that getting bigger or smaller?
No, you're lying.
It's growing by a significant amount each year. All right. I noticed too that it was increasing, but I also noticed that it was increasing exponentially. Yeah, so that is to say, it's not increasing by the same amount numerically, well, like arithmetically each time. This grew by 60, but then this grew by 69 bunnies. So the amount it was growing was growing. Okay, so what was the initial measured value of the bunny population? 400, good. So there's our initial value. That is where I started the stopwatch. That's where I started taking note. That is time 0, not time 1, time 0. So we're going to just like associate that with the x value 0. And I could have x values going down the side here. You could improve my table and just have some like x values there. Values. Okay. Now, what percentage is the population? Yeah?
I have the answer.
What was the answer?
8.6.
8.6? What?
Percent.
Is that, how did you do that?
I did 400, 460 times 100, and then 460 divided by 529 times 100, and they're both 8.6. Right?
Oh, that's very interesting. Let's see. I think you got 0.86. If I do 400 divided by 460, I will get 0.869, so 0.87. Yes, times 100. So that would be 87%,
No.
I'm afraid. And here's what's happening. We did 400 divided by 460. Is this number bigger than 1 or smaller than 1? Yeah. What? If I have 400 cookies and 460 people sharing the cookies, it's kind of like a rough party, isn't it? It's a little bit like, okay, we've got to carefully ration our cookies so that everyone gets some and no one's getting a full cookie if we're being totally fair. I don't want to go to that party, but I just imagined it. I just went there, everyone. So this one is going to tell us the percentage decrease going in that direction. But we are noticing that the population of bunnies is increasing. 13? This is close, but not quite. So if we do here, 460 divided by 400. Let's try this one. 460 divided by 400 is 1.15.
That's the answer?
Well, that's 1.15. So what's that telling us? The question asked was, how much is what percentage is the population increasing each year? What? 15. I see 1.15. Shouldn't that be like 11.5 or something like that? Why 15?
Because, I don't know, I divided 60 by 4, but I think that's the wrong way to do it.
Actually, if you did 60 divided by 400, that would give you 0.15, which is the same thing. Convert this decimal to a percent?
Times about 100.
Yeah, so it's 15%. This one here, 1.15, if I times it by 100, what do I get? I get 115%. Okay? So, there you go. It's increasing by 15%. So let's put in a little sentence there to make that clear. The population of bunnies is increasing by 15% per year. All right? Let's do a little experiment with our calculator and see what happens when I take this number 1.15 and multiply it by 460. My goodness, it perfectly predicts the next data point. All right, so if I take this one, this one and multiply by 1.15 or 15%, I get the new population the year later, 15% greater. Okay, so that's kind of cool. All right, so that is how we do this. Okay, you're going to take the two values and divide them. It will give you the percent. If you do this and say, I can see that there's been 60 growth and divide that by 400, you will get the percentage growth without the 100% in there. Is that a hand up? No? Okay, cool. We can chat later.
Is it increasing by 1.15, 15, or 115?
Yeah.
If you multiply by 1.15,
Yeah.
you will have one whole of what you had the previous year plus an extra 0.15. In other words, if you multiplied by 115%, you would have 100% of what you had the previous year plus 15 more percent. The two are the same. 1.15 is 115%.
And then what about the 15?
The 15 is just how much is it growing by? Okay, so yeah, if I told you that my pants were 20% off when I bought them, that would mean that they cost 80%. 20%, sorry, 100% minus 20% would be the price I paid. Or if I told you that the place I bought my pants paid 100% and then they sold them for 150% of what they bought them for. I paid 150%, they added 50% to 100. Okay, so we're always adding on to that 100% there. So next we're interested in the growth factor of this situation. The thing that this growth factor, what that means is we're going to build an equation that looks like y is equal to a times b to the x. In these types of equations, a is our initial value. The amount of bunnies at time 0. And b is the growth factor. So we want this number b. Okay? And here is the mini formula that you can always use to calculate b. b is equal to 1 plus the percentage increase or decrease. Okay? So in this case, b is equal to 1 plus 0.15 equals 1.15, which also equals, by another name, 115%. Percent means take that number and put it over 100. So 115 over 100 is the same thing as 1.15. It's just a different way of showing you. It's like me saying, here's the back of my hand. This is also the back of my hand. Same back of my hand. So now we got this B. We already had the A. So now we want to take this A value, which is 400, and then our B value, which is 1.15, and build an equation that can model this situation. What does the equation look like in this case? Well, it will be something like this. There will be an equal sign in our equation. What's on the left side? Yeah, the population of bunnies, which is y. It can be expressed as a times b to the x. What's my equation look like? A is the initial value, b is the growth factor.
400 times 1.15.
400 multiplied by 1.15
And x.
to the power x. where X is the number of years since 2023. All right, cool. And Y is bunny population. Very cool. Now, let's use our model to predict the bunny population in 2027. What will X equal in this case?
4.
Cool. So just plug and chug. Y equals 400 multiplied by 1.15 to the power 4. Okay, it's a function, so we're just going to input X. That's our input. Or it's definitely within our domain. 4 years is a reasonable number of years to use this model for. So we're just going to do that. 400 multiplied by 1.15 raised to the power 4 equals. We will have 700 bunnies. So in 4 years, the bunnies went from 400 to 700, growing at 15% per year. Very good. In 4 years, if it was growing like a line and only adding a flat 60 bunnies every year, we would expect 240 more bunnies. We got 300 more bunnies. It's like an extra year of growth over and above the line. Okay? So let's put our data points on here. Okay? And then we're going to figure out this question. How long will it take before there's 2,000 bunnies in my neighborhood? All right? Here's our initial value, 400, 469, a little over 500 there. We just calculated 4 was 700, so that would be like there. Now, what else would you want to do to start getting a sense for what this does? Maybe it does this, like I don't know, maybe it could do this. What can I do to find out something over here? Sure, you tell me what. So we're going to go X and Y and fill in a little table here. That's a great idea. So let's do, how about the even ones? How does that sound? 6, 8, 10, and 12. And now we're just going to punch it each time. Clear. 400 multiplied by 1.15 raised to the power 6 equals 925. Was it 925 or 926? 925. Okay. Now I'm going to just do, I could do 400 times 1.15 raised to the power 8 equals. Oh, we're getting closer to 2,000. 1224 to the 10. 1618. There, we're past. Okay, so 2140. A lot of bunnies. We're going to be overrun. Okay, so 925, we're just going to go put that on there. That's a little bit higher than 900. 8 was 1224. That's a little bit higher than 12. 1200, that is. 1618, that's a little, ever so slightly higher than 1600. And 12 was 214, that's up there. So now we can see that it's gradually increasing, and we can use this graph now to estimate when we're going to have 2,000 bunnies. So I go ahead, and I'm not trying to join them with a straight curve. Still not doing a very good job, but I'm trying to curve and do that. And now I would guess that that would be about my answer, don't you think? I just go ahead and look for the point where this crosses the line y equals 2,000. There's the line y equals 2,000. It's crossing there. That looks to me to be, well, here's 11 years. I would say about 11.5. Wouldn't you, based on this graph? Okay. If you would like to know how to algebraically solve for the exact value, you need to take grade 12 advanced functions to solve for an unknown exponent in these cases. But we don't care. We're happy to use guess and check or graphing to get a very good answer. Let's test the answer we found and see how accurate it is. Okay. So we're just going to go back and, oh, what's happening with my computer here? There it is. We're going to go back and use our calculator and just punch in 11.5. So we're going to go multiplied by 1.15 raised to the power 11.5. We're already comfortable with the idea that exponents can be in between the values. For example, this is in between the 11th year and the 12th year. Somewhere about halfway through the 11th year, we expect it to be about 2000. And we get the answer 1995.6. 1995.6, that would round up to 19 of our target. So we're pretty good. Maybe next I try, if I want to get a little closer, now I can use guess and check. 400 multiplied by 1.15 raised to the power 11.5. Let's go 5.2 and see. There we go. We're just a little high. So we think it's probably like 11.515, something like that. It's where we can zero in and get really close. But that's already within one bunny of our target. So we could say that's after 11.52 years. And so we add 11 to 2023, so that's 2034, around, assuming I started measuring this around July. If I started measuring this in January, which would be a weird time to measure bunny populations, but hey, here we go. There. And those are all the things. Those are all your skills. Can you use graphs to represent these situations? Can you use tables to not only build graphs, but we also used a kind of table-based solution to zero in there on 11.51. Okay? And yeah, can you solve for the growth factor? So in these cases, to solve for the growth factor, we have to use division of two of these lines. And we want to have a good prediction of what size of number we are expecting. If we're growing, we want a number bigger than 1 when we do that division. If we're shrinking, we probably want a percentage less than 1 in order to get that. So, in your teams or individually, answer the questions on the back sheet. We will take them up at 9. Go. Number 4. Let's talk about question number 4. The population of a deer. Oh, that reminds me a little bit about my population of bunnies. Okay? Except, unfortunately, unlike my... Oh, yeah, it's frozen. Let's unfreeze. Unfreeze. Okay. Unlike my bunnies, this one is decreasing at a rate of 2% per year. So we are 100% minus 2%. That is to say, we will have 98% of the deer year after year. So if I write that as a decimal, I just shift the decimal place twice. There's the invisible decimal that I move there and there. Boop. Okay, so that's going to be 0.98 is our growth factor B. Okay, so that was in 2008, so that's when x equals 0. Okay, and here's our initial value. A equals 240. All right, so now we go ahead and build our function. Y equals a times b to the x. Or in other words, y equals 240 multiplied by 0.98. See where we got that number? Yeah, it's good. All right, good. Raised to the power x, where x is the number of years after 2008. So if we want to predict the number of deer in 2015, that's x equals 7. The way I did that was 2015 minus 2008. That gives us the x value of 7, the number of years since 2008.